and a warm welcome to this workshop. We are very grateful to the SAIF facility from IIT Bombay for giving this opportunity. So today we are having a workshop on the HRMS. Okay. So before we start, we have a good number of audience here. We would like to know, if you handle mass spectrometer anytime. So you can just raise your hand if you are used mass spectrometer. Quite a few, so that's good. So that's what we have decided. We will start with the fundamentals, so that the later topics becomes easier for you. Okay, so we are going to start with the fundamentals. So in this session, we are going to talk about the basic fundamentals of mass spectrometry and also about the high resolution mass spectrometry. And then my colleague Dr. Daksharat and Dr. Sridhar will come deep dive into the application part. So we are going to cover the applications for persistent organic pollutant, food authenticity, and also in pharma applications. So we have a mixed crowd, so we will try to touch upon different applications, different segments of the market. So let us see the fundamentals of HRMS. So what is mass spectrometry? So it's nothing but a molecular balance. Okay, just to weigh your molecules. So it gives me the molecular weight of my molecules. Okay. But one important thing about this mass spectrometer is you require your molecules in gaseous phase. Okay. It should not be in a liquid phase. So your molecules should be in gas phase, and that is possible only when you bring them into the gas phase. So a mass spectrometer can only work with charged particles. That means either positive charged particle or negative charged particle. So you have to bring these molecules into the gas phase by ionizing. Okay, so we ionize these molecules and we bring them into the gas phase. If it is an LCMS, you are using LC as a mobile phase. So your molecules are in liquid phase. You have to remove this mobile phase and get those molecules in the gas phase. In case of GC-HRMS, you are already using gas. Okay, so it's not that difficult to get these molecules in the gas phase because already you are using gas. But one thing is very important, we have to charge this molecule, ionize this molecule, to get these molecules in ionized phase. Okay, and what we are measuring is the ions. Ions will have a certain mass, certain charge, and based on those properties, mass to charge properties, we separate those ions. So this is the basic definition of mass spectrometer. So what is it used for? Okay, it is basically serving two purposes. One is for identification. So if there is a sample or a molecule, so people will ask me what is there in my sample. So I would like to do an identification. What is in my sample? So identification is one of the important applications. And once you have identified what is this molecule, you would like to quantify it. Okay? How much of each of these molecules or compounds is present in your sample? So we do a quantitative analysis. So identification and quantification. So when you are doing identification, you would also like to know what are the elements present in my molecule. Okay. So that I can do the proper confirmation for a particular substance or a molecule. So basically, a mass spectrometer, any mass spectrometer, can be a GC-HRMS or an LC-MS or an SPMS. So as I said, the first component has to be ion source because mass spectrometer can work only with charged particles. So first is the ion source, and then once the ions are generated, then we have the analyzer to separate those ions. Okay, so analyzer is nothing but different types of mass spectrometer. So whatever ions you have formed, you have to separate that. So the analyzer separates the ions based on their mass to charge property, and then you have the detector to detect this. So your sample will be introduced either through a gas chromatograph or a liquid chromatograph. So you have an inlet, you have an ion source to produce ions, and then analyzer to separate ions, and a detector to detect those ions. And everything is controlled through the data system. Okay. So in case of LC and GC, we have different types of source. The purpose is to create ions, charged particles. Okay. So in case of GC, we have two sources, electron impact and chemical. So we have to create ions, so we have EI and CI source. Okay. And in case of LC, we have the ESI or the APCI or the APPI. So basically, the purpose is to create ions. In case of GC-HRMS, EI, that is electron bombardment, electron impact. So we bombard these molecules with electrons to create ions. And the analyzers are of different types. So you have most commonly used analyzers are quadrupole. So most of you must have heard about quadrupole based instruments, single quadrupole, triple quadrupole. And then you must also heard about time of flight. So Orbitrap is one of the technology which is patented by Thermo Fisher, which is a high resolution technique. So we are going to talk about the high resolution mass spectrometry. So if I look into a basic mass spectrometer, so you have this ion source. You can see the ion source here, the first component in a single quadrupole system. So we have the ion source here, you produce the ions, and then we have the main quadrupole, the analytical quadrupole, which will separate the ions based on the M by Z values. So the analyzer is the second component, and the third is an electron multiplier or a photon multiplier, which will detect those ions. So three components. And this whole system has to be under vacuum. Why vacuum is required? Because we want the ions which are formed to travel and reach the detector with minimum collisions with atmospheric gases, okay, so that you get signal for those ions. So if you have atmospheric gases, if vacuum is not good, then those ions will collide with the atmospheric gases and your ions will never reach the detector. You will not get a signal for those ions. You want signal for the ions of my interest. So there is a field which we are applying, the electric field here, which will sort the ions. So the quadrupole, we apply the electromagnetic field and it gets separated. And what is the information that we get from the detector? We get the mass spectrum. Okay, the spectrum is nothing but a plot of mass to charge on the x-axis, and the y-axis is the response of the detector or the abundance of ions. This is a mass spectrum in EI for a very notorious molecule, which you can say is for cocaine. Okay, it's a fingerprint of cocaine. So when I do a GC-HRMS EI spectrum, cocaine will give this spectrum. Anywhere you do, say fingerprint of the molecule. So this is a very important tool or a very important identification source. So this will never change anywhere. So you do go and do this analysis on any mass spec, anytime, this is not going to change. So all chemicals, all molecules have a unique EI spectra, which is a fingerprint of that particular molecule. So what you're seeing right now, as you can see, is that they are in integers. Like say the ion is there, the biggest ion is 82 and the second is 182. So they are integer masses. So what spectra you are seeing is called as nominal mass spectra. So all these ions are nominal masses. Okay? But now we are dwelling into high resolution. So you can say the molecular ion of cocaine, which is 303. You can also see that. So it gives me a lot of information about my sample. If I study the fragmentation, I can even deduce the structure of my molecule. But what are the challenges that we face in mass spec? So why we have to go into high resolution mass spec? One of the biggest challenge that we face is separation of isobaric species. Species having very close molecular weight. Okay, now if my molecular weight is 182.123, another one is 182.125. then the unit resolution or the nominal mass spectrometer will not be able to separate because its minimum resolution is 1 atomic mass unit. So it will identify both of these components as 182. So these close molecules, having very close molecular weight, is not resolved in a nominal or a low resolution or a quadrupole based. So we require something more. So isobaric species. So we call this species as isobaric. Sometimes different molecules may have elemental composition which is looking very similar, but structurally they may be different. So when you are going for a nominal mass, integer masses, it's very difficult to separate. So that's one of the biggest problems that we are facing. And sometimes your sample may be having a huge background. You may be doing a very dirty sample, a very dirty matrix, and And when you're looking for your components of interest, those components may be masked by the background because the sample is so dirty that you are not able to see your peak of interest. So in such cases, the nominal mass spectrometer or the low resolution mass spectrometer fails miserably. That's the reason we are going towards high resolution. Now, I just want to give a simple analogy here. This is an image. Okay, I've taken using my old mobile phone. Can you identify this image? Which structure it is? It's looking some sort of orange color, some images there, but it's a very famous structure. Some people will identify like Radha has already identified it. So this is something. It's a bridge, very famous. But I've taken a low resolution image. My old mobile phone, having not much high resolution capacity. But if I take the same image using high resolution, I can clearly see what is it. It's a Golden Gate Bridge in San Francisco. So what it tells me that taking a high resolution image gives me more information about the subject, about the sample. So it tells me there are some vehicles on the top of the grid. I can see the cloud. So a lot of information just by having a high resolution image. So you must have also seen our telescopes, like James Webb telescope. So they want high resolution image. So we get more information on the sample, from the object. So similarly, when I'm going for a high resolution master, I get more information about my sample, more inputs, which will help me in positive identification. I can remove the false positives. False positives is where the substance is not there, the molecule is not there, but still you identify that molecule. So false positives can be eliminated. So when I say resolution, what is resolution? So resolution is the ability of the mass spec to distinguish ions which are having similar masses, which we call it as isobars. So there are a couple of definitions. One is called as a doublet method. So most of your mass spec, the lab that we use single chord or a triple chord or time of flight, they use a singlet method. So what is singlet method? So this is the singlet method. So this is the peak mass spec. So we take the peak width, 50% of height, and we measure the mass. So m upon delta m. So you can see the delta m, if you extrapolate it, is 500 minus 0.05 minus 499. So we are subtracting this and 500 divided by 0.1. That gives me the resolution power at the peak width at half maximum. So that is coming around 5000. So this is the normal resolution power of a quadrupole base. But there is also a different mass spectrometer called magnetic sector, which uses a doublet method, which is used normally for high resolution. So when you have two peaks of very equal masses, the value between them should be at least 10%. This is called 10% value definition. But most of the mass spectrometer will use the singlet method, which uses peak width at 50% of that. Okay. So this is what we are going to use for all the mass specs. So if you are talking about time of flight, if you are talking about orbit track, which we are going to talk, they use this method, singlet method. So one is resolution. And why is it important? So as I said, high resolution will remove the interferences out because you can pick your needle from the haystack. So high resolution, we'll see some examples. So it will remove all the interferences. And high resolution also gives me the true mass, the accurate mass of the molecule. So normally we calculate nominal mass, integer masses. But that is not the exact true mass. So high resolution gives me accurate mass, true mass up to 4th or 5th decimal. Okay. So accurate. So that will help me in getting the elemental composition of the molecule. So this is one example. You can see that these are two pesticides having different structures but different molecular weight. Okay, but the difference is only 0.0138. So the molecular weight is 292.02, other one is 292.04. So using a low resolution instrument, which is 15,000. Normally for a triple quad is around 5,000 to 8,000 to 10,000. I'm not able to separate these two isobaric species. But as I go on increasing the resolution power to 35,000, those I see some peak separated. And as I go to 50,000, I can see a baseline resolution. So resolution power separates the isobaric species. And then at 100,000, clear-cut baseline separation, just by increasing the resolution power. So the benefit you can see here, so isobaric species can be separated using resolution, high resolution. And say if you have a very dirty background, now this particular on the right that you're seeing is a nominal mass spectrum, like in your single core or a triple core. The top photogram is total antibody. So I'm looking for iprodium, which is a 10 parts per billion in a leak sample, which is a vegetable. So its ion, unique ion of iprodium is 340. So I extract 340 extracted antibody. I see a lot of humps. I'm not able to see my peak because the background is giving a lot of interferences, which is 314, containing 314 ion. It may be 314.12, 314.15, 17, whatever. But the window of that is 1 delta. So anything from 3.5, 314.5 is all shown as 314. But the same data on a high resolution mass, I just give the accurate mass. You can see I have given in 4 decimals, 314.0094. So it just picks up your data from the background. So interfering species which should have masked your data just gets removed by using high resolution. This is another example. 2 species having very close molecular weight. So this is, and you can see the peaks are co-eluting, the green one and the yellow one. But at resolution power of 10,000, you see at different positions of the peak, you are not able to see. But at a resolution power of 100,000, you are able to clearly see the resolution, the separation at different locations of the peak. So very clearly separated from each other. So what are those high resolution equipment? So you can see anything above 10,000 is considered as high resolution. Anything below resolution power of below 10,000 is a low resolution. So magnetic sectors start with 10,000. And then you can see high resolution TOF, and then orbit starts from 60,000, goes up to 1 million, 10 lakh resolution power. And then the FTIC here, and there is Fourier transform, ion cyclotron resonance mass spectrometry. So these are all high resolution mass spectrometry. But when we talk about resolution power, we also need to know what is accuracy, mass accuracy. So whenever you are talking about high resolution mass spectrometry, there are 2 terms which are frequently used. One is resolution power, other is mass accuracy. So mass accuracy is nothing but mass error. How much close you are to the true mass, the theoretical mass. More close you are, better for identification, better for predicting elemental composition. So this is given by this formula. Mass error is exact mass, which is theoretical mass minus measured mass divided by theoretical mass. So we are converting that into ppm into 10 to the power 6. So lower this value, that means you are very close to the true value of the molecule. So this is very important. So that, why it is important? Because when you are very close to the exact mass or the theoretical mass, it gives you the correct elemental picture of the molecule. So you can see here. So when we see hydrogen, we normally consider hydrogen as 1. But its exact mass is not 1, it is 1.007. Similarly, carbon. Okay. So you can see that carbon has 2 isotopes in nature. C12, C13, C14 is also there, but its amount is very less. So C12 is almost 99% and C13 is almost 1%. So every molecule will have C13 isotope. Like if I look at sulfur 32, 3 isotopes. 34 is 4.4%. So if I get a sulfur molecule, I should be able to see this isotopic pattern. So in a low resolution equipment, you will not be able to see this isotopic pattern. So you can see for halogens, chloride and bromide and iodine, they have those isotopes in the exact mass and the nominal mass. So we normally go by nominal mass. So the high resolution will tell you the exact mass and the exact elemental composition. So mass measurement depends on the resolution. Higher resolution gives me higher mass accuracy. So you can eliminate certain elements if those isotopic peaks are not there. So it helps in finding out the structure of the molecule. So you can see here the mass accuracy of some of the instruments. So you can see here the Orbitrap is having a very good mass accuracy between 0.5 to 1 ppm. Lower the values, better is the mass. But if you look into triple quad or iron trap, it's very poor. Okay. So what is the advantage? So when I am doing unknown samples, where I don't know what is my sample, lower the mass accuracy, the value, that is below 1, the number of possible formula is reduced. The number of possible candidates for that particular molecule is drastically reduced. So if I have 4 or 5 ppm, the number of proposed chemical formulas are huge. So the analyst or the chemist who is working has to deal with so many molecules. But if the mass accuracy is good, below 1 ppm, then there are either 2 or 3 molecules, and then you can pinpoint what is the molecule present. So you can see here another way. Okay. Below 1 ppm or 2 ppm, it's very good. We can eliminate so many other substances. So this is one way of showing, like say the resolution power is 15,000, then the mass accuracy for some of the species goes up to 9 ppm. But when it is 60,000, it is below 1 ppm. And if it is 240,000, it is below 0.5 ppm. So they are very, very close to the true mass of the compound. So resolution power, more the resolution power, better is the mass accuracy. Now, we have heard about GC-HRMS. So there is also a targeted acquisition which is done in quarter 4, GC-HRMS. Okay. So we are doing targeted analysis. So MSMS is like this man who is fishing with a rod, is catching a certain type of fish, a particular analyte by using this fishing rod. He is not catching all the fish. But when you are doing Orbitrap analysis, high resolution, what we are doing, we are catching all the fish in the pond, and then we are segregating the data. So we are not leaving anything else. We are doing a full scan, we are scanning, we are getting all the information about the sample, and then we are doing the data analysis. Okay. The advantage here is I have all the information available, and then I can segregate my data. So just looking at the instruments, and then we will go to some of the unique applications. So Orbitrap instrument is available both on the GC front as well as on the LC front. The Orbitrap instrument is the same, only the resolution power changes. So in case of GC, you can see here, first this instrument will launch in 21, and in case of LC Orbit they will launch earlier. So this is the current model. The first Orbitrap was launched in 2005, okay. And the first GC Orbit was launched in 2015. So it's now almost a mature technology. So the instrument that we have in IIT Bombay is Orbitrap Explorers GC, which you will see in the practical session. So it's a very compact instrument. On the right is the gas chromatography, and on the left is the mass spectrometry. So there is one more model which is having a resolution power of 240,000. So you can see here, as your sample complexity increases, you require more and more resolution power. So at least 60,000 is bare minimum required. So you can do a structure elucidation. You can have different applications like metabolomics, extractable leachables, pharma, industry research. So when you don't know the structure, it's better to start at least having a resolution power of 60,000 with MSMS capability. And you can see this is the sensitivity that you will get. scans, the sensitivity is 6 femtogram in full scan mode. So normally you get femtogram level in triple quad, in MRM or SRM. So this is very sensitive. You can go to very low levels of detection and also very high levels. So these are some of the specifications. I'm not going into detail about this, but the main workflow that we are doing, which is very important, we are just doing full scan. There is no method development involved. Setting a method is very easy. I give the start mass and end mass. I start from, let's say, 50 going up to 500. I just tell the instrument, just scan from 50 to 500. Full scan, that is, I'm catching all the fish in the pond. Nothing, I'm not leaving anything. So when I'm doing this analysis full scan, I can do all 3 types of analysis within one run. That is expected compounds. That is, I know there are some targeted lists. I want to find out those targeted lists, like your triple quad. So targeted analysis, expected. Suspected compounds. So I have a database of 100, 200 compounds, and I can screen against the database and find whether those compounds are present or not. So suspected compounds, and then totally unexpected compounds, where you don't know anything, unknown profile. So in just one injection, I can find out all 3 of them. That's the power of high resolution. Expected, suspected, and unsuspected. Just by doing one injection. And the best part here is, since I have captured everything, okay, I can do a retrospective data analysis. What does that mean? That means I can go to my data at any point of time in future. Like say after 6 months or 1 year, some percentage, so I have to check for this particular analyte. This particular peak is expected. So in other instrument, you have to do the analysis again because you have missed that information. But here, since I am doing a full scan, the whole information is there in this particular data. So you have to just give the accurate mass of that particular species. So given 4, 5 decimal, just pull the data out because you have got all the fish in the pond. You have all the information available within your data. You have to just give the accurate mass and just pull it out. So you can see the applications that we can do. Huge amount of applications. And my colleagues will cover those applications. So my colleagues will cover PCBs, POH, persistent organic pollutants. So different applications can be covered. So extractable utilities, pharmaceuticals, analysis for, especially for impurities which are having isotopic, like you must have heard about nitrosamines in certain drugs. So one of the impurities was dimethyl formate. This is an impurity which comes at the same time as one of the impurities, NDL. Okay, the isotope peaks of DMF interfere. So this particular instrument could resolve the isotopic impurities and can remove the false positives. So right now we look into the instrument hardware. Like how does, any question? Yeah.
With the targeted quantification?
Yeah, targeted quantity, this one, targeted quantitation, left, right? So that means, let's say, let me give an example. Like you are exporting grapes. Okay? Now, European Union has made a list of targeted elements. Like this pesticide should not be present. It should be all below 10 ppb, let's say. So you know the list. Okay, what Europe has banned. So you have a list of targets. So you take your standards, you quantify them. So targeted. So you are finding those pesticides which are banned in Europe. Okay? But that doesn't mean that the food is safe or the grapes is safe, because it may have some pesticides which you are not targeting. Like say you are importing food into India. You don't know from which country, let's say some X country you are importing, but they must have used a certain pesticide which is banned in India or which you are not aware of. But it is being used there. So you don't have in your targeted list, so you miss it. So this particular analysis will also find out what is the missing component. So that is the unexpected. So in Europe, most of these labs, they do the total profiling because they get samples from all over the world, like food stuff they import it. And they want to ensure that the food is safe. Just this is one example that I'm giving. So they screen completely known and unknown and then ensure that the food is safe. Okay? We are not doing it. We are just doing targeted analysis. There is a list of pesticides which we know and we target those cells. It doesn't mean that the food is safe because we are not targeting the unknown species. There may be certain compounds, certain components which must have metabolized, which must have degraded, which may be equally toxic. We don't know. So this instrument helps you in finding out those and finding those unknown as well. So this is the explosive GC which you will see in the lab. So orbiter is actually not a single analyte, it's a hybrid instrument. So we call it as hybrid because it has got, let's get the pointer on. This is the source here, and then it is a hybrid instrument which is a combination of the quadrupole and the orbiter. So you can see the orbiter is here, and the orbiter size you can see here, it sits in your palm. Okay, the new generation is still small, high field orbiter. It's like your 10 rupee or 20 rupees. It's a very compact size, but it requires so many other things. So introduce ions into the orbiter. Okay, so you have the S-shaped ion guide. So you have the ion source where the ions will be produced, and when ions are produced, there will be also a lot of neutral species, which we are not interested. If they go inside to the system, they will increase the noise level. So we are giving a bent part. So the neutrals are not charged. You don't have either positive or negative. So they move straight and they hit that rod. And they are eliminated. So only the ions can take the positive ions or the negative ions. And then they go through the quadrupole. So quadrupole allows you to filter a cloud of ions or a range of ions, some sort of sample preparation. Then it goes to the C trap. So it is coming with a certain kinetic energy, those ions. So we need to cool them, reduce the kinetic energy. So we have nitrogen gas in the C trap. So it will cool these ions. And then it's ramp up the voltage. So we want to introduce into the orbiter. So the ions, we ramp the voltage and we inject into the orbiter. But there is also one more device, ion routing multiplier. So if you want to do NSNs, okay, so you can send those ions to this part, do a collision, okay, give some energy, kinetic energy. So they get collided with nitrogen, and then those collision products can be sent back to the orbiter. Okay. So what happens inside the orbiter? Let's see. So when ions, this is inside the orbiter. So this is what we are looking at, this part. So we are looking into what is happening inside the orbiter. Okay. So the ions are injected into the orbiter. So we squeeze the ions from the C trap to go inside this orbiter. So it has got 3 electrons. One central spindle-shaped electrode and 2 barrel-shaped electrodes. So when the ions are injected at certain tangential velocity, it has got some velocity, it is injected. It's like a planet orbiting sun, our Earth. So it goes inside. So the voltage is, we ramp the voltage of this central electrode so that ions are attracted, but it has got a certain centrifugal force. Like Earth is rotating around the sun, but Earth is not going inside the sun. So it has got its own centrifugal force, which is compensating the voltage. So it starts rotating. Okay, but once it starts rotating, it also starts oscillating. So we ramp this voltage, it starts oscillating. So back and forth, the ion starts oscillating. Okay. So it has got 2 motions. One is the rotation motion, and the other one is the axial rotation. So it oscillates. So when it oscillates, each packet of ions, let's say each M by Z oscillates with a certain frequency. Okay. So the lower mass ions comes very close, and the higher mass comes little higher. So all these ions are at different levels. So they form a packet of waves. They start oscillating. So when a packet of ions oscillate, so you have these two conductive surfaces. So when your positive ions oscillate, so this conductive surface, on the surface will have electrons. So they are getting attracted. So they are also forming a current. So they also start moving. So what we are doing is we are inducing an image current on the end cap. Because when the ions are moving, because the electrons in the conductive surface, they are also affected. So they are also moving. So without ions hitting this surface, we have introduced an image current on the surface. This image current is a function. Okay, is in the time domain. So it is compared to this oscillation frequency. So it is matching in this frequency. And you can see the different rings, they start oscillating. Each of these rings induces an image current. Okay, and it is matching with this oscillation frequency. And this frequency is related to its mass. Okay. So we get combination of ions. There are a lot of ions oscillating. We get a bunch of rod transmitters. But it's a mixture of all different ions. So we want to break it down. So we use Fourier transform mathematics. It's the mathematical engine that we use. And we break it down to individual sine waves. Because it's an alternating current which is getting formed. So we break into individual ion time space. And from the time domain, we convert that into frequency domain. And frequency domain, this frequency is related to square root of k by m by z. So we know the frequency, k is the electric field constant. So what is not known is m by z. So we know both of these, so we get the constant. So we can measure this frequency very accurately. Okay. So this is the image current detection. So the advantage of Orbit is we capture these ions. So we can do a lot of oscillations. So we can measure it very precisely. That's the reason it gives you a very high resolution. Because in other mass spectra, the ions just fly. You don't have time to study those ions. But this is a trap. And we have all the time to study those ions and get higher resolution. So even close isobaric species can be resolved because we can spend more time to get this done. So this is one more example. C12HHS. Okay. So lethal molecular weight is 184. Exact mass is 184.03. So if I am doing a full scan and I expected a single core, I am giving a window of one Dalton, one atomic mass, 183.5 to 184.5. So I get almost 38 peaks. But when I use Orbitrap, 184.03413, I don't get any other peaks. I just get my peak. That's the problem. And there are a lot of identification points. So this is one of the data. So this is accurate mass accuracy of less than 5 ppm mass accuracy. This is as per the international guide. So whenever you are using high resolution, mass accuracy should be at least plus or minus 5 ppm. So you have retention time standard, you have fragment times, you can take ratios of that, you can have isotopic pattern. So we have a lot of identification points which are not available in a nominal mass spectrum. So this is the source of the mass spec, which is wire free. Since it is wire free, you can remove the source. You know, you are doing a certain experiment, you have done a full scan, now I want to do a CR, chemical analysis, soft analysis. I can change the source without breaking vacuum and do the analysis. Can even change the form. These are some of the features. I am coming to some key applications. You know, my colleagues will cover those applications, but some typical applications which you may not have heard. You must have heard about e-cigarettes, which is getting very popular. A lot of youngsters do vaping and all. But you know, is it really safe? So we wanted to find out what is there in the vaping solution, in the liquid. So using high resolution, we try to find out what is there in this solution which is used in e-cigarettes. So we are using headspace. So headspace is nothing but we can keep the liquid here, and when you incubate this vial, the volatiles come in the gaseous phase, and then you transfer this vapor, keeping the matrix down. So GC is suitable for volatile species, and you can inject it. Okay. But here in IIT Bombay, we have a facility which is more sensitive than this head. It's called as solid phase microextraction, SPM. Okay, so this facility you'll see in the lab, which is nothing but, vial is the same, we incubate this vial. So volatiles come in the gaseous phase, but we have an SPME fiber which is exposed to this volatile. So this fiber is nothing but having certain adsorbent. So this adsorbent will capture this volatile and to increase the concentration of this volatile. So normally in headspace we inject 1 ml, but here the sensitivity will be 6 to 8 times more. Okay, and then this fiber is injected into our cell. So this is the instrument with SPME fiber. So this is the tool that we are using, which is triclosan, which can do liquid, headspace and SPME. You can change this tool automatically. So this is, you can see the fragrance profile. So in case of normal headspace, it's a static headspace, you inject only 1 ml. Okay, like colleagues from pharma will know, they do always 1 ml injection. But here in SPME, you are concentrating those vapor on the fiber. So you can see that same injection, SPME mode, you can see a lot of peaks which are not seen here. And then the dynamic headspace, comparing to the dynamic headspace. So you can see many species which are missing in a static headspace. So this facility is now available at IIT Bombay, and we use this for the e-cigarette liquids, and we could identify these are the conditions that we are using, and we use full scan. As I said, in GC already you can always do a full scan. We isolated compounds, we measure those to the library, and we confirm. So these are some of those flavor which we analyze. Some of the major peaks we identify using HRMS. So we are getting exact mass, high resolution filter score, and similarity index, reverse search index. So using all these tools, we could find out what are those species present in this e-cigarette liquids, which are equally toxic. And we could easily identify, you can see the same injection, Jane lemon flavor, e-cigarette liquid, with EI, PCI, and NCI. And we can confirm the molecular weight very easily by changing the source without breaking vacuum, get more information. And one more application which is becoming very popular now is breath perhaps. Okay. Breath perhaps is what? You analyze the breath of the sample, of the patient, and vapor tells you a lot of story of the disease which is existing in the patient. It's a totally non-invasive technique that we are using. So a patient or an individual, when breathing out, exhales a lot of VOCs. Okay? And they contain a lot of information. They tell you the current metabolic state of the individual. Okay? Genomics tells you like which disease is predisposed, but it doesn't tell you the current state of the body. But when you are exhaling the volatiles, the metabolites which are produced from the body, and once you collect it and analyze it, you can find a pattern. Okay? So each individual has its own pattern. Healthy individual, patient suffering from cancer, and disease set in, metabolism change. The volatile profile is exhaling out change. So if you study this profile and compare it, you can find out those biomarkers and you can predict those diseases. So early detection can be done, and then the right medicine, right time can be done. So you can use this tool for precision knowledge. So when you breathe out, there are more than 1,000 volatile organic compounds which are breathing. And this is a totally non-invasive technique. So when you are going to a lab, pathological lab, they take body tissue or blood sample, which is invasive. You feel the pain. Okay?
But when you're breathing out, it's a totally non-invasive. You can go to the patient's house, a small kid, and just sample his breath. So, the source of VOC can be endogenous within the body, or different organs gives out, but it can be also exogenous. That means from the environment, from the food that we use, medicines that we use, or the exercise that we do. Okay? So it is a complete phenotype of the individual. Gives you information about that particular individual. Not only endogenous, but also exogenous. So this is the breath test you can see here. So the person is inhaling, and we have an absorbent cartridge here. So we sample this into the cartridge. So there are pressure sensors which will do this. So these are some of the references available where they have done the breath transfer. So the whole blood takes just 1 minute to completely circulate through the blood. And the blood from whole body gets exchanged. It gets exchanged at the lungs. So whatever it carries from different parts of the body. The volatiles get exchanged with the air we inhale. And when we exhale out, those metabolites are coming out. So we can sample this air for 10 minutes. That means we are concentrating the air which is coming out and then injecting. So these are some of the references where the breath biopsy has been used. And these are some other references. So you can see major big institutes like NHS, Mayo Clinic, they all use this technique for finding out these different biomarkers in particular disease. So you can see most of the cancers, tuberculosis, breath biopsy is used. And you can see the research publications which has increased, and it has increased tremendously after COVID. COVID is also a pulmonary disease. You can see here. So VOC publications and the clinical trials using breath analysis has increased. So what is the solution? So we have a breath biopsy station, and we connect the breath. Take those cartridges to the thermal desorption unit, and then find out the unknown species by using GC Orbitrap. Create a database. So right now it's used as a research tool. Okay, we are creating a database. Okay, some of the organizations in India have this facility, and also in Europe and America people are using it and using Orbitrap to create this database. So there is a volatile organic atlas. Atlas is created for different diseases. So this is the breath biopsy station. So it can be taken to the site of the patient. It's a totally non-invasive and using GC Orbitrap. So just concluding because. So once you find out, like you profile the VOCs and you find out the biomarkers, and then once the biomarkers are done, you can do a quantitative analysis. So with this, I'll just conclude because we start with application. So we are creating this accurate mass library for different disease biomarkers, and you can predict and quantify. So this is some of this compounds from the breath biopsy. Okay, it is external dividing. So two models of Explorers GC, that is Orbitrap GC. It's a benchtop equipment, so it has got the productivity, high resolution, and flexibility for introducing different samples. So with this, I conclude my presentation. So if there are any queries, any questions, I will be more than happy to answer.